approach that kind of uses some statistical techniques or tricks or whatever you want to call it to separate out partition survival in the river and estuary from the ocean. Go to the next slide. So we work on protected salmon, and their survival is really dictated in the ocean. It's really, the main factors affecting survival in a salmon's life cycle occurs in the ocean. So we really want to be able to, if we're modeling ocean survival, be able to get a better handle on what the factors, conditions are that are affecting them. And current approaches don't take into account, even though we have tag recoveries from avian colonies or birds eat the fish that have pit tags in them and they deposit them on colonies, that data often isn't being used in terms of smolt-to-adult return models. So we just want to be able to use the best available science and all the available data to be able to build better models for ocean survival. That's really the motivation for this. Next. So a little sidebar here is some background information. If you're not familiar with pit tags, which are passive integrated transponder tags, and they are activated by, well, when they go through an electromagnetic field. So it goes through a reader and it sends off a radio signal that tells the reader what the unique code is on the tag. These things are pretty small, like typically for smolts, they're like 9 millimeters we use. And there's these things, the same thing that they inject in pets, and so if you lose your pet, they can scan it and figure what it is. And so there's a steelhead smolt there that's getting injected with the pit tag, and the dams on the federal dams on the Snake and Columbia River all have, not all of them, all but one are set up with a system. You can see here with the picture with the pipes and the white pipes and the readers there. That's at Mary Dam, I think. And so the fish will go into the powerhouse and shut it through these screens that go up in the bypass system, and they go through pipes. And then the tags need to be pretty. I mean, now there's newer technology where you don't have to be in such a close space to the reader, but anyway, so we can read the tags at dams. Going through the bypass systems, we have it has a towed array. You can see the net. There's a matrix array that we use to detect tags in the estuary. And that allows us to get survival. We estimate survival through the hydropower system, the Snake and Columbia River. It allows us to get survival to the bottom of the dam. And then we also recently have installed Lower Granite Dam in one of the spillways readers so that fish can get the technical number. So pit tags are widely used in the system. They're very valuable. They're long-lived, and they can be retained in the fish for a lifetime as long as they don't shed the tag. And we recover them. Well, real-time research has a big program of recovery tags, doing bird surveys at colonies all over the Columbia River Basin. And then we can detect them in the adult ladders as they come back up through the dams. So we have quite a system. Detection is almost 100% in ladders, not exactly, but through the dams going out, it's in recent years with all the spill, it's much less, but we still can get information from it.
So remind me how you're tagging ESA listed species in the first place. Was this out of hatcheries or?
Yeah, a lot of it's hatcheries.
Are these co-located or the actual listed species? Because I'm not a salmon guy, but I hear a lot about natural versus
Yeah, we tagged a number of natural origin fish.
Okay.
I mean, there's tape limits on it, so
okay.
there's limitations on how much you can tag, but yeah.
But most of it's from hatcheries.
Yeah, it's majority is probably hatchery, yep. Okay, next.
It sounds like they are having trouble hearing you. If you speak up a
Oh,
little.
really? Okay, so maybe I can just sit over
Yeah, if
here.
you want to sit over here closer to
Okay.
it.
Okay, so this is the kind of the study area. So the smolts are going, think of steelhead, Chinook, salmon, coho going out to the ocean, passing through the Snake and Columbia River. And the last dam that they encounter is Bonneville Dam on the Columbia River. And you can see that, so I have it in blue, they're detected as juveniles going out. And then they pass down through the estuary and past that, I had mentioned we have those boats that tow the array, detection array. And then they passed, there's some avian colonies, double-crested cormorants and Caspian terns in the estuary where tags can be recovered from the juveniles. And then they go to the ocean, depending on the species, however many years, 2 to 4 years they spend out there, and come back and then can be detected as adults at Bonneville Dam. So, okay, go ahead to the next one. So this is the same kind of, this is kind of our diagram of that, kind of this now looking from the Washington shore, basically. So juveniles are going out across Bonneville Dam, coming from the left, go across the total array. And this is kind of the cartoon of, we're going to use this diagram throughout here to kind of describe various components of the model here. So I'll refer to these things probably in different ways, but between Bonneville Dam and the total array, I'm going to call that the river reach. And then from the total array to this kind of imaginary line at the ocean entry, there's no detection there. That I'm going to call the estuary reach. And then the idea is to partition the survival between, from the river, the estuary, and the ocean, partition those apart. Okay, next. What's traditionally been done, and I mean, there have been some other studies that have used the mark-recapture approach, but typically what's done for smolt-to-adult return models from Bonneville Dam or from Granite Dam is basically like a logistic regression. Did you return or not? And because detection is pretty high in the adult ladders, you can kind of treat it as a like 100% so detection. So a logistic regression has often been used, and in that case, you're pooling together what happens in the ocean and what happens in the estuary, and because those birds can have they can have a big impact. Their predation rates can be quite high in the estuary, and so if you don't account for that, you're kind of coloring or clouding, I should say, clouding the signal of what's happening in the ocean.
But presumably phi is a function of year in these models anyway, right? That constant. You got it as phi adult, but I mean it's phi adult year of release or something like that.
Yes. Yeah, year of release. So everything's kind of indexed on migration year, the year that they enter the ocean. Okay, next. So phi is survival here, and this is, I'm just showing it in terms of the components of what that phi adult is for a given year. I'm not showing the index for year or day or anything here, but just in general, partitioning the river, the estuary, and the ocean. And then even further, we can use the information on the years that they spend in the ocean. So, if it's, and the probability, you can assign a probability. This gets a little bit difficult because these things can be quite confounded, and this maturation, probability of, maturing and returning. In the simplest way, you could just say that it's kind of predetermined and it's the same every year. there's some proportion that come back as after 1 year, after 2 years, after 3, after 4. And but there's a benefit to splitting these out in that you can isolate the particular conditions in the particular years that fish were in the ocean. So like 2017, 2018, and 2019 had very specific conditions, and that could be very different than 2015, say, which was poor ocean year. So being able to isolate those years instead of putting them all together gives an advantage into estimating how the conditions affect survival. So this is just kind of the way to think of a way to visualize this. So on the left, I have the first year they enter the ocean is typically the hardest. I think so. They're getting hit by predators pretty hard. There's could be issues with the food availability and so on. So the first year survival is going to be treated a little different from the remaining years in the ocean. But you can see on the right then, if the idea here is that when you have shared experience across these cohorts as they enter the ocean. So if you look at the diagonal, those years on the diagonal, the same color, are shared among these different cohorts. So you have there's some
year effects, not year by cohort.
Yeah, assuming year effects, and in this case, yeah, there's year by cohort. I think that the assumption here that I'm going to use is that the first year has a different impact than the remaining years, but okay, they're being shared across the cohorts. Okay. And then further, using temporal stratification within seasons, so like stratifying on day at the Bonneville Dam, day leaving Bonneville Dam, day passing the trawl. I'll call it the trawl or the towed array. So by further stratifying temporally, then you can capture these changes that happen through time. And for mark recapture models, it's an important assumption that that you have a constant detection probability or survival probability within the time frame that you're estimating. And if you don't, you can bias in particular, like you have non-constant detection probability, you can bias your survival estimate. So the detection probability at the total rate can be quite variable because they don't operate it continuously. And so it's important to be able to account for that. And then also we know that bird predation rates change through time, and the timing of when fish enter the ocean is really important. So to be able to account for time within season is important to better estimate these effects. And then the last thing is accounting for the tag recoveries on the bird islands allows you to separate out, as I said, separate that mortality from related to the birds in the estuary from mortality in the ocean. You can see why, if we go to the next slide, why that's important, because this is the proportion of steelhead that were recovered on East Sand Island, tern and cormorant colonies over time. And you can see that there's been management, there's been hazing, there was a year when eagles came and scared a bunch of birds off, and so it changes through time and it's been declining. And if you're not accounting for that, you could be confounding it with what's happening in the ocean and clouding your ability to estimate what's happening in the ocean.
So these are actually recovered, so they're removed from the population, as opposed to at the towed array where they detected and
right.
not removed.
These are dead.
These are dead.
They're known dead, yep. And not all will see that. So a bird can, catch a fish in the river and eat it And then there's a probability that it actually takes it back to the colony and deposits it on the island. And then once it's deposited on the island, then they go out in the fall, just one time, because they don't want to scare the birds off after they're gone from the colonies. And they go out with detectors and, you know, they try to find tags out there. And then there's a probability that you actually find the tag given it's there. So these are the observed tags. So this is the minimum proportion of fish that were eaten by birds, right? This is only the ones that we observed.
So what is the proportion of steelhead recovered?
So of steelhead known alive at Bonneville Dam or the toad array. So they were detected.
Okay, so they're detected at Bonneville, no, the toad array?
Well, the way you can be either detected at Bonneville first or the toad array, but either one, if you're known alive at one of those, when you enter the system.
Okay.
Yeah, that's what it is.
So this is the proportion of the ones that survive at least as far as Bonneville.
Yeah.
Possibly the toad array.
Yep.
But haven't entered the ocean.
Yep. Yeah, because they're feeding kind of, I mean, they probably go to the ocean a little bit, but they're mostly feeding in that estuary area. Okay.
That's far more than I would.
Yeah, it's a lot. And that, I mean, it could be as much as 30–40% actually the predation rate just from that colony. And then you think that once they get to the ocean, you got shearwaters, you got hake, you got all kinds of stuff hitting them once they hit the ocean. So it's a feeding fest. Okay, so this is just kind of describing, so I already said that Bonneville Dam, there's the juvenile bypass system where fish can be detected. And then there's something called the corner collector, which is down in the right corner there. It's like a chute that shunts water from the surface on to the side of the powerhouse tube. And there's a big pit tag detector in that thing. That went in 2006. So we have fish detected entering our system, what we're calling our study site or whatever, at Bonneville Dam. They're detected there. We're going to stratify it by daily. And I don't really point this out, but they can also be first detected at the toad array and enter the system that way. Okay, next. And so I'm going to kind of, I don't want to go too much details on, but I'm going to show, like, you know, almost all of these things are going to look the same. There's some logit or some transformation of the parameter, survival, detection, recovery probability, so on. And it's going to be some linear model with random effects and some priors. So I may not go into all the details, but just keep in mind that these are all kind of be similar. But so what we're looking at here on the graph. Oh, I stands for year in this case.
Okay, so it's year.
Yeah, year, and then bold is vectors, so they're, or matrices, so they're, the day is not being shown as an index here. So this is, you're getting within year, you have a vector of survival probabilities across the days. So for each day leaving Bonneville Dam, there's a survival probability, and that's what that graph is showing, how that changes over time. And that's just the simulated data. So, okay. And then same thing for each day leaving Bonneville Dam, then those fish have a travel time distribution, or another way to see it is an arrival probability. They have a probability of arriving on a certain day, passing the trawl, whether they're detected or not. So they're all given, they all share this arrival distribution for each particular day, and that changes through time. So it can depend on covariates, flow, day of year.
I haven't put any covariates in this. Oh, your view depends on.
Yeah, the mean travel time depends on covariates, and actually, I didn't show it there, but I think that, yeah, then that variance, the spread, the variance in the travel time can vary on covariates too. I didn't show it there, but. So this is kind of key. So this allows in the model to, even if you aren't detected at the total rate, because there's a probability of arriving on different days, you can integrate over those, arrival probabilities and the conditions that were occurred at that time, and you can kind of get like a weighted average for the fish that aren't detected at this particular time. And all these things, survival, and if you're never seen again downstream, you're kind of integrated over all the possibilities. Okay, next.
Sorry, I love equations. The gamma is just a constant independent of the covariates by year.
Yeah, that's basically a random effect for year.
Right. So is that it's a random effect. But is it identifiable if you don't have a total array other than the estimate of 0? How would you?
Oh, if you didn't have a total array, no, you.
The total array is, sorry, I'm looking for indices. So this thing depends on year, but not day, because day would be non-identifiable, I would imagine.
Yeah, I mean, you could put a random effect for day, but
Well, I don't think you could. That's what I'm saying. So if this is just a function of year, not
it's a function of year, yeah.
okay.
Yeah. Yeah, just to kind of absorb variability that's not explained by the covariates, right? And then similarly, detection probability at the total rate. And this is important because they don't operate the thing 7 days a week. They don't operate it 24 hours a day. So there are definitely periods of 0 detection probability. And then depending on the hours in the day, that varies too. It's not always the same. And then there's things like flow and other conditions that can affect where the fish are. So and how they behave. So we can make that a function of covariates too, and allow it to change through time. Okay. So now this is one of the interesting parts, and that Quinn Payton at Real Time Research came up with this kind of idea of being able to, because they do all this stuff with the avian tag recoveries and predation rate estimation. So this is kind of comes from his book here, how I'm doing this. But so this is assuming that, let's say theta sub E is the mortality probability in the estuary. And if we assume that there's additive mortality, then we can separate mortality due to bird predation from colony 1, say the terns, and bird predation from colony 2, the cormorants. And then what other mortality that we can't directly account for or observe, but it's there. So we're going to split that into those 3 categories, and then just based on, okay, then we call phi sub E the survival. So of course 1 minus phi is the mortality, and then there's this nice relationship that falls out of that the sum of the survival and the mortalities is equal to 1, obviously, but that helps in modeling, because we can make that a simplex and have it sum to 1, and we can separate those things out if we have data on each component. Okay. So then we'll let this parameter zeta sub j, where j is indexing the colony, and this is just forget about time, and this is just kind of generally to introduce these concepts. But so let that be the probability that the tag is deposited. So a bird eats the fish and then actually deposits it on the colony where it can be found, and then let psi sub j be the probability that it's detected given it was deposited there. And then you can separate out, take those mortality components from each bird colony and say, okay, there's the proportion of that mortality that what we observed basically, it's because it was deposited and detected, and then there's a proportion that we don't observe because it wasn't deposited and or wasn't detected, and then that allows us to isolate the part that we can observe, right? So then that zeta times psi times theta there's a probability that the tag is observed on the colony, given that that fish was alive when it entered the reach that we're describing this for. Okay. Yeah, and that's basically just showing that the blue is the part that you can observe and the red is the part that you can't observe directly, aside from, you know, piecing it out from the mark-recapture model, you know, the estimation of the survival component.
Is phi z ever identifiable compared to the ocean mortality probability? How could you split those by the time you don't see them again until
Yeah,
the
it's good question. Good question. Yeah, so this is something where there's some assumptions that you can make that make it easier. You're right, you cannot separate that out, but you can assume that, okay, what's happening in that part of the estuary is very similar to what was happening upstream of the trawl.
Okay.
Even though it's not going to be the same, if you make some assumption that, okay, these are going to share the same covariate relationships, share those parameters, and then you can constrain it to be a little more identifiable. It's still not identifiable completely, but it's partially identifiable, I would say. Okay.
Yeah, I always find when I read mark-recapture models, you can make it so complicated, and you say, what data do you actually have to pin this? I mean, you can write down the probability experiment easily, but you can't, you know, when you sort of match it against data, you particularly with the way, you know, you're seeing partial observations and their mortalities, and
yeah, that's why I said at the beginning, there's some kind of trickery here. You got to make some assumptions to make this stuff work. And I think that the key is in making reasonable assumptions and then using priors too. This is an example. So they go out and they did deposition experiments, which were difficult, but you know, they would like have some pool or some, I don't know exactly how they did it, a pin or something where they had fish, and then these gulls and terns and cormorants would come and get the fish, and then they would estimate what the deposition probability is. And it's they're kind of, you know, it's not perfect, but and then every season they go out and they'll sow, you know, spread known tags out on the colonies that they're going to survey, and then go out and recover them at different times during the season. Because, you know, the wind, there can be waves and stuff that wash them away, and so on. It's like, so the closer you are to fall, the easier it is the more likely that tag is going to be detected on the island. So there's a function of the recovery or detection probability of the tags on the island. And so we use that information and make informative priors in the model then based on data. That allows us to estimate that predation rate or mortality due to each of the colonies. Okay. And so here's some more formulas. So this is kind of the cool part about this. So now if you can estimate these predation rates, the theta, using a multinomial logit. So what I'm doing is taking so this predation rate will change through time, recovery rate changes through time, deposition rate is going to be, I'll show you in a minute, it's just that one's assumed to be a constant. And then we can share, well, I was saying, you can share the parameters from the river survival in terms of this baseline, what I'm calling phi sub z, baseline survival before predation, and then just use this multinomial logit, and then these things, the survival and the mortality sum to 1. So it looks nasty, but it's actually it's pretty straightforward. And then we create this false, or you know, this line of ocean entry where, again, sharing this is another assumption that could actually be probably improved. There are some acoustic tag studies that look at travel time through the estuary and out into the plume and into the early ocean, the travel time, so, and survival. So this travel time could probably be improved by using that, but what I'm doing is just basically taking the migration rate or the travel time model from Bonneville to the total array, and then adjusting it for distance and using the same covariates to estimate arrival probability at the ocean. Okay. Yeah, and this goes back to the colonies. The slides are probably out of order a little bit, but yeah. So this comes from Hostetter et al. 2015. They published some, and they use this all the time. They came up with parameterization for priors for deposition probability. So one for the terns and one for the cormorants. Terns are more likely to deposit on a colony. The cormorants and gulls are much less likely, but there aren't gull colonies in the estuary, so we don't have to worry about that here.
So this is given you caught it, eaten it, what's the probability it ends up at?
Yep.
I presume that's somehow you've got to get a fish into a tern.
Yeah. It's a,
I guess that, I mean, if it's pit tag, you at least know what you're getting back.
yeah.
Because you know that animal has to.
Right. Yeah. So those, yeah, I think what they did is they had some net pins or something, and they had all these pit tag fish in it, and then they saw what the probability, estimated what the probability was over many different colonies and stuff. So it's not perfect, but that's why they're kind of wide priors. Okay. And then, as I mentioned, so this recovery probably is given that the tag is on the island, what's the probability that your equipment is going to detect it? And so this is through time. So they have ocean entry. So the longer that tag's been sitting on the island, the more likely the wind's going to blow it. It's going to get covered up with dirt or whatever. It's going to make it less likely that. So the closer you are to the fall, when they do the surveys, the more likely the tag's going to be recovered. And it's interesting. They go out every year and they recover tags. They're still recovering tags from 10, 15 years ago that were never detected before. So it's yeah, it's not perfect. So yeah, okay, next one.
I wasn't expecting that lower detection probability.
Well, I don't know if it is. It can be quite low, actually. This is just for graphical purposes. That's not a real.
Oh, okay.
Yeah,
That's not the estimate.
No, sorry. It's just that was just to make a slide. I did that before I had actual data from the colonies. And if you don't have this, well, okay, for the simulation, I do some simulations, and then I didn't, at that time, I didn't separate out the deposition and recovery probabilities. So just put them together in the same. Yeah. You can account for these tag recoveries without trying to separate out mortality specifically. I mean, without trying to, yeah. You can pool those three parameters can be multiplied together, and you can still have it inform survival, but I'm not worried about that here. Okay, next one. And then, so there are different ways you can do this, but if you assume that, one way to do it is assume that, okay, there's some predetermined probability that fish are going to come back after 1 year, after 2 years, 3, and so on. And you can just, those sum to 1, use a Dirichlet distribution that works well, and have it be constant across the years. I thought that would be the only way for this to work, and maybe it is, but
these are products.
These are priors, and yeah, this isn't directly. I mean, you do have data on the year, how many years they spend in the ocean. So, but you can actually allow this to vary by year, and I would imagine that you could tie this to some covariates, probably more likely individual covariates like size, which is probably a pretty good determinant of how big you are when you enter the ocean. How likely, it could affect like how many years that you're going to spend there. But I didn't try to do that. these are really, this is really confounded with survival, right? Because all you observe is the fish that come back, and you don't know what. Anyway, so you are able to account for probability of coming back at different age, and you allow it to be constant or vary by year. Okay.
You have a question online. Matthew Vincent asked, how do you know whether these later detections are from dead fish as juveniles that are missed or as adults after returning from the ocean?
On the bird island?
Birds be eating, the fish will be eating birds.
Yeah, those birds are only eating juvenile, they're only smolts. I mean, only pelicans will be able to eat smaller adults, but were they referring to
I'm not sure.
the bird island recoveries? Yeah, and
Even 1-year-olds, it could be too big to eat.
Yeah. So I don't know if they're talking about,
Yes,
so, oh, the bird islands, okay. So there is, we've kind of been getting into this a little bit. There is some juveniles do go down the adult ladders. I wasn't sure if you're talking about the pit tag detection on the way back. So for Chinook, there are mini jacks, and they will come back in the migration year, precocious males, and they'll be detected on the ladders, and they may fall back across the corner collector. So you have to be aware of those things, but and juveniles can go down the ladders, but it's fairly rare. So yeah, I mean, we can determine if it's an adult or a juvenile for the most part. Okay, so we're going to allow survival in the first year in the ocean to be different from the remaining years in the ocean, and in that the main thing is to allow it to be a function of daily covariates, and day is actually so there's like you can get daily upwelling, daily flow out towards the estuary, and these can affect the size of the plume. I don't know. There's all kind of things that can affect their.
Is this the day it leaves the ocean? Because obviously,
Yeah.
This is the day of ocean entrance. You're assuming is determining survival in the ocean.
Yeah. And it's actually, I mean, Mark Sherrill and Rich Zabel years ago had a paper that showed that it's really day and day squared, and it can vary by year. It's pretty a big determinant of and, that's a proxy for what's going on out there. And I use day and day squared in here too, with random effect on both of those by year, and then try to. I don't like doing that because I'd rather, that's representing something, other things that are going out there. So the more that we can, this allows you to look at then, okay.
Right. I guess what I'm saying is, and I know you guys do that, but why just the day of entry into the ocean? If you're out there for 4 years, this is the first year of survival. Survival is integral over the time you're out.
Right. So this first year includes there's going to be shared covariates, like ocean conditions, whatever. I'm using just some principal components over multiple things, but just to simplify for the purposes of just trying to see if this stuff would even work. But so there's some kind of annual level things that are in this first year that are shared with the other years. And then there's the kind of I think most of the mortality is happening right when they get right as they enter the ocean, because they're there's shear waters, there's hake, there's all kinds of fish out there that are hitting them, and then I think that's the biggest hit. What's that?
In the plume?
In the plume.
Oh.
I think that's a big part of it. And in the early ocean, when they're young and they're just getting hit by predators, So, and that's what most people have assumed in the past, is that that first year survival, the conditions in that first year, you can just ignore the other years, and that's going to determine their adult return probability. Okay. How are we doing on time?
10:15.
Oh, you're close.
Yeah.
Okay.
And more important, it's more interesting in the meeting.
Okay, so then so however many years you have spend the beyond the first year, then those are all, varies by year, but that all has the same, just based on annual ocean conditions, basically, and with random effects for years, that because you can't, it's really variable, and a lot of those things don't really explain much. But okay, so this is some fabricated data, but just kind of an idea, like so each row would be a fish with a particular migration year, juvenile migration year, in the year that they're entering the ocean, and then you have like the day they were detected at Bonneville, and if they were, and then the day that they were detected at the trawl, where 0 is they weren't, and then did you show up on bird colony 1? Did you show up on bird colony 2? And then how many years did you spend in the ocean if you returned, and the 0 if you didn't? That's the observed data. Aside, I mean, that's the observational data. Then you have the covariates, the daily flow, temperature, turbidity, just daily upwelling in the ocean, and so on.
There's a likelihood for each of these components for every single pit tag individual.
Yeah, there's a detection history,
right?
And you can collapse, since there's not there's the day part. So basically, collapse on day, and then there's you can.
Oh, there's multi-node.
Yeah, we'll get to that. There's a slide. Yeah, a couple slides on that. Okay, let's go. Yeah, okay, so here. So this, if you're familiar with mark recapture, this could be thought of as the probabilities underlying an M array. So these are, as you go across the row, those cell probabilities all add up to 1. So this is a multinomial distribution. So each row is an independent multinomial distribution. So you can have, then for associated with each one of these cell probabilities is a count. So, given however many, let's just say, just ignore day for now. Let's just like if you collapse across all the days or something, just one cohort, basically. You have the number that were released, which the numbers aren't shown here, but then you have a number that were detected at the trawl of those. And if they weren't detected at the trawl, then so each one of these is a different outcome, right? Okay, you weren't detected at the trawl, but you were recovered on colony 1, or you weren't detected at the trawl, you were recovered on colony 2, or you weren't detected at the trawl and you were seen as an adult, and that will split that out on the next slide, or you weren't seen again. And then the next row, you can take the number that were detected at the trawl, and they become the starting number as the number released for that row. And you can add in fish that were not detected at Bonneville, but they were first detected at the trawl, and that put those two together, and then you have another multinomial distribution described by those probabilities. So if you go to the next slide, then.
It's not a problem that some fish will have 2 likelihood components. If you've seen in Bonneville, then you invoke.
No, it's not a problem, because you're conditioning on. So yeah, so there are each row does share some fish, right? So the fish that were detected at the trawl all end up in that row on the bottom, right?
You have a question online. I'd like to hear about the methodology of bird colony tag detection. Person with metal detector, pit array.
I think, I'm not exactly sure how they're doing it now. They used to pull like this sled or trailer thing behind it, lawnmower or something, a tractor, and then and it would go across the ground and scan them. But I think they do use like it looks like a metal detector. It's a pit tag wand that's like a metal detector. You know, I think they use that too. I don't know exactly how they do it now. It depends on where they are, because there's the Astoria Bridge, and there's a bunch of cormorants nesting on there, and they're going out there and detecting tags on that too. And I think they're just doing it with wands and stuff. Okay, so this is taking that adult thing and splitting it out. So you have basically, you know, the probability that you stayed 1 year, that's the pies, are the probability of staying number of years in the ocean. And then you just multiply together okay, if you're in the 2 years in the ocean, then your survival is the first year times the second year, and so on. And then if you go to the next, and then you have the probabilities of never being seen again, which, you know, you can just do one minus the other probabilities and get this, but just to be thorough and make sure you get all the possibilities and stuff, you can write it all out this way. Okay, so just to test whether this even works, you know, it's better do a simulation and see if you can recover the parameters that you use to generate the data. So this is just, I'm just going to show one simulated data set where released 25,000 fish over 20 years. And, you know, just as we described, survival detection, avian recovery, 30 by year, and with covariates. And then this is all, you know, Bayesian framework, fit and stand. Okay. And so I'm just going to boil this all down to basically a couple slides here. So the different colors are different components. So the top is the river survival between Bonneville and the trawl, then survival in the ocean. Well, I guess I didn't. Yeah, that's the river survival. Those parameters are shared across the river and the estuary, right? So then survival in the ocean, first year, survival in the ocean, the remaining years, avian mortality, recovery probabilities, detection and travel time. So different components, and the top one in each category is the intercept, and then there's slopes on the covariates. And these are all just standardized, just random, you know, covariates that they weren't really actually measured things, I don't think. So you can see one thing that stands out immediately is the intercepts. If you look at the intercept for survival in the river, survival in the ocean, they're lower than, you know, than what generated the data. So these are all, if it's on that center line, then it's basically unbiased, right? So, but if you're off and you're not being captured by the credible interval, then you're a little off, right, from what was used to generate the data. Hopefully this wouldn't occur over multiple data sets, and I haven't looked at that, but I think it's clear that you would expect this to happen in some respect, because we're not actually able to completely segregate the estuary survival from the ocean survival. So you can see that the river, the river one is probably colored by the estuary. So you have first year survival and river survival, their intercepts are lower than expected, and then the ocean survival is higher than expected. So
did you look at your posterior samples to see if there's a correlation? I mean, looking at this, you think it's just compounding between the two different sources.
Yeah, I haven't looked very closely at that. I mean, it is, and you.
That's what it smells like.
Yeah, yeah. I mean, you would expect it to be, and so I think there's room in here for investigation of how you could potentially improve this somehow. Maybe you can't. Whether it's, you know, using data from acoustic tag studies or somehow tightening priors or something. I don't know, but the main thing is that aside from the Beta River 2, probably at least the ocean survival slope parameters are pretty much right on, right? And that's what we want. I mean, if you can estimate what are the covariate effects, what are the things affecting ocean survival, and you can still, I mean, whether you're off on kind of the intercept may not be that important as long as your prediction, when you put all these components back together, and then you're able to predict adult return better. That's the main thing. So I feel like it's not that big a deal to be off on those intercepts as long as the combined survival, when you go to predict it coming back as an adult through the whole cycle, if you're on with that, then I think that's.
Do you have that, the measure of total survival for an animal released on a particular day? Because that's the ultimate performance metric, right? So of animals that were vulnerable that left, what's the probability of coming back after a certain number of years?
Yeah, and I mean, that's what it's fitting to, right? So that's the data that it's fitting to. So I would expect that is going to be on. I haven't looked at that, but I'm just based on how those intercepts are, and I just believe that it's going to be, it's fitting to the return data itself, and it's trying to figure out what's happening in between and not doing it perfectly. But some of those other parameters are detection probability and travel time are very well estimated.
I mean, the inverse question to that is if, and I'm sure you'll do this, but if you ignore the avian mortality component of the model completely, how well, what are you gaining by putting the?
Okay, yeah, so I did do that, and I didn't include that in here. That was one of my first questions is, okay, what are you gaining by doing this, right? By doing that and the age component, segregating, does that even do anything for you? But what happens is when you don't do the avian thing, it makes it even harder to segregate the ocean from the estuary. You just, that's allowing you, that piece is what's really allowing you to try to separate at least some amount that estuary from ocean survival. And you get those, the slope parameters get even further away from the line by quite a bit, actually, when you drop out the avian mortality and age. Okay. And so this is that beyond first year ocean survival. So so that there's the true value that was used to generate the data in the simulations, and then there's the estimated posterior median in blue, and then there's credible interval in light blue. So it's tracking closely, but you can see that the intercept is off. It was estimating well for this, but it's still, it's still pretty close. For not being able to do this before, right? Before everything was collapsed together. With first year and everything, multiple year survival into one thing. Okay. And then this particular simulation, I allowed the age distribution to vary by year to see if it can even do that, and surprisingly, was estimated fairly well across there, which I really didn't think that this would be identifiable. But it probably was just a function of the number of years I had in the simulation and the number of fish in each year. Okay. So now apply this to steelhead. I also have done it for Chinook, but it's not, that was recently, and I haven't summarized it. So steelhead are hit a lot harder by the avian colonies. They have a lot more tags recovered. So there's a lot more information from the avian colonies for steelhead than for other species. So that was one of the reasons I wanted to look at steelhead. One disadvantage is that steelhead mostly come back in 1 to 2 years, rarely 3. So you don't have a lot of that age, time stratification in the ocean to help separate out the ocean things. So Snake River steelhead migration years 2004 to 2019 with additional years in the ocean. There's a tern colony and the cormorant colony that on East San Allen that this data comes from for the tag recoveries. And that we got data from Alan Evans and Quinn Payton at Real-Time Research they use for their informative priors for deposition and detection probabilities on the colonies. And then there's covariate relationships that I'll explain in a minute, random effects by year. Okay, next slide. So yeah, so quickly, so for the river survival, there was flow, temperature, turbidity, distance, and a year effect. Travel time had flow, distance, day, and year effect. Detected probably at the trawl. Like I said, the hours of operation are pretty critical to that, and then flow and a year effect for all these year effects are for kind of absorbing things that the covariates are. Then I could definitely do other models for avian predation. I just used day and day squared, and that was, yeah, separate intercept by year, and that could definitely allow that day and day squared thing to change by year, but for this, I didn't do it. And then that first year ocean survival has the daily things of flow, upwelling, flow by upwelling, day and day squared, and then random effects by year for day and day squared. And then PC1 and PC2 are principal components on these annual suite of annual ocean conditions that Brian Burke had come up with in the past. So I was just using that to simplify things. And then those PC1, PC2, and the year effect are shared between the two with the ocean survival. Okay. So this is data. So I'm going to show a couple slides here of data. So this is the number of fish at Bonneville or the trawl in each one of these years. So there was like around 1,000 in 2004 and 2005, and then it's a lot more because detection improved at Bonneville. I think that's why. And then it's been variable across the years, but with like 2010 at like 45,000 or something like that fish. So there's a fair number in some years, but I don't show the number returning, but I could go to the next slide, in a couple slides or so. So these are numbers in 2010 at Bonneville Dam, just so you can see, okay, this is what the distribution of fish is across the season, starting like April 10th through, you know, June, mid-June. Okay. Okay, so this, okay, so in blue are the proportion fish returning, collapse across all the age classes in each year. So that it's low. I mean, you're usually less than 2%, around there, as low as, you know, 0.5%. And then like 2008 was the best year of that lot, and that was over 6%, but it's not a lot of fish coming back, right? And then I used this, you know, I don't know if you've seen this stoplight thing that,
Brian's thing?
yeah, Brian's thing. So just the ranks of the, across the years, basically you're ranking based on a suite of ocean conditions. So you can see 2008 was the best year, and then, you know, there was kind of a period there, 2006 to 2013, basically, that were kind of good years. And then after that, another run of poor years. And then if you look at the next couple of years beyond that, those are better ocean years beyond 2019. Okay, and then this is the age distribution. So in each year, the proportion, the blue is 1 year, gray is 2 years, and red is 3 years. So you can see it's really kind of rare to stay 3 years in the ocean. And it is varying over time, with more recent years, more likely to have fish staying longer. But this is colored, confounded, or a product of survival too. So it's not just maturation probability. So, you know, the survival probabilities in the different years are going to make these bars different. So, okay, next. And then we already saw this slide, but this is the proportion recovered, proportion of the tags recovered of the fish known alive at Bonneville, basically, that were recovered on the avian colonies, which changed over time. Okay, now we can see some results. So this is, I'm just going to show 3 years, and these were kind of, these are across a range of years. So 2008 was like one of the best ocean years. 2015 was one of the worst. That was like the blob, you know, ocean temperatures were terrible. Anyway, so
This is an interesting plot to me because we've never really been able to look at this, or we just never did it. Daily detection probability, because detection probability at the trawl, you have to have, you know, information what happens afterwards, either being recovered on a bird island or seen again as an adult. And I didn't think we could estimate it this well. I mean, it's, so the dark blue is the posterior median, and then the light blue is the 95% credible interval. So we're estimating it quite well, based largely on hours of operation.
I was gonna say, how much of this is hours of operation?
I think it's a lot of it is driven by that. And then I think flow was the other covariate. That's the only covariates I used in here, I think, was flow and hours of operation.
Amazing how precise this is.
I know. But it's, I think this is critical to being able to, you know, get the travel times, the times of entry to the ocean and so on. Okay. And then this is more variable, but this is predation rate for turns in those 3 years. And this is just using a day and day squared with the random intercept by year, I think. Okay, and then the next one is cormorants, which I was kind of surprised that their estimated window of predation time is a lot narrower than the terns. But then if you go to the next slide and you put those together, the effect of those on, this is estuary survival estimated. Which, you know, 2010, there was quite a few fish, I think, and so it's fairly well estimated there. But 2015, I don't think, maybe there weren't as many island recoveries in 2015, or maybe the deposition, the detection, probably the tags on the islands was not very well estimated. I don't think, something like that. That makes it more noisy.
Can you help me a little bit in the previous slide?
Uh-huh.
To work out how, I'm just trying to think through how you are able to estimate a day-specific predation probability when you don't know, you only get your returns once a year.
Right. So yes.
Is this because those are the animals that were passing at that time?
Yes. So I'm using basically the time that they're passing the colony.
Right. So
The time that they're arriving at the ocean.
Pass later in the year in the data. Sort of. Yeah. Okay.
Yeah. So that's where this is where the temporal stratification by travel time is critical to allow this to happen.
That's right. Okay, I see it now. Because if you hadn't had the temporal thing, it wouldn't have known when those animals passed. Hence, that you should have seen day 185, but you didn't, because they were there, but you didn't see them in the recoveries. Okay.
So there's,
very cool.
and they're pretty when they're going through that section of the river, they're going through pretty quick, and they're not that spread out. So, and I think that's why those travel time parameters were estimated spot on in the simulation. It's good that you can estimate that fairly well, and then it's very useful.
Once you've got that, then this suddenly becomes.
Yeah. And the same with the first year ocean survival, that helps with that too. So next one. So these are the estimated parameters for ocean survival, and they're shared for the first year. The blue ones are shared for the first year and the other years, and then the green ones are just informing first year ocean survival. So you can see the flow and the upwelling, you know, their significant flow by upwelling was not, and then day and day squared are really driving this relationship. So there's a lot of stuff that's kind of being represented by day and day squared. That's not, I mean, we need to go and find what those things are. And, you know, one thing Brian Burke was telling me was like, you know, there's shearwaters are out there, but they're not out there at the same time every year. And we actually have some citizen surveys that they've been going and doing every year for shearwaters. And we could use that information, like the timing of when shearwaters arrive, and maybe an abundance estimate of shearwaters. There's other components that we can add to this that will help, so you don't need to rely on just day and day squared, which are quite, there's no predictive power in that really, especially when you have a random effect on those that changes by year. Okay. And then this is estimated first year survival for those 3 years. So 2008 was one of the best years, and 2015 was one of the worst years, and you can see it in that first year survival. And surprisingly, I mean, it's able to separate out these things. Now, whether, I don't know, again, the intercepts on these things are going to be kind of a little bit interchangeable with the intercepts on the later survival, the remaining years, but it is able to, because of that, those arrival probabilities at the ocean, you're able to kind of piece this stuff out. Okay. And then this is the predicted ocean survival for each particular year. And again, putting those ocean conditions below, and you can see, because we only went through 2019 for those, for the previous plot, and this has those remaining ocean years, which got better. And it actually shows that the period where there were good conditions, like between 2006 and 2014, it's reflected in the ocean survival. And then when it gets bad in 2015, 2016 shows poor ocean conditions, but that 2016 survival estimate is higher than I would have expected, but it does, for the most part, this line kind of tracks what, this includes annual random effects too, and so it's not completely being driven by the PC1 and PC2, but it is at least tracking. And actually, PC1 pretty much is this.
I was going to say, to what extent is this model just reproducing what Brian produces?
It is, yeah. Well, it does. It's that PC1 component reflects this red light, green light thing pretty well. Okay.
I believe you saw this in E1 table, something like that.
Yeah, right.
I don't even know where it was. This is one of the Pacific Council. I don't know if this was steelhead, but it's obviously USA.
Right.
We do get Ryan's which informs the process.
Yeah, yeah. And then this is the predicted age distributions. I didn't put uncertainty on here just because it would be messy, but it kind of reflects, what the data showed. So a little bit higher probability of staying a little longer in the ocean in recent years. But okay, and then I don't know. I mean, it does allow, let's say, an approximate partitioning of estuary and ocean survival. And it gives you a little bit of ability to kind of separate these things out. I think it is an improvement over previous approaches. I mean, just the fact that you're accounting for that bird predation is an improvement. And I didn't.
Do you have the previous slides without the avian piece, just to see how the answer, what would be robust and what would be with the uncertainties? Obviously you can't predict things like predation rates and stuff because they will disappear. But for some of the other things like survival, ocean survival, what do the credibility intervals do if you don't have that component? If they get much larger, and basically, again, going to this earlier point about what the value of these extra data is. Basically, the question is, with the onset change.
Yeah, I did do simulations early on. It was over a year ago when I was doing this, and I just haven't been able to pick it up. But it was in the earlier iterations of this presentation, I was showing that. The one thing I do remember is that when you didn't include the age stratification and the avian recoveries, those slope estimates were really far away from, in the opposite directions. I mean, it really, you're off on, and it's just, and of course the intercepts change. So
I was thinking, what if you go back 2 slides, like the time, the day function, maybe not that one, perhaps, but this sort of stuff, how would that, because ultimately you've taken out avian predation
Yeah,
before you got there. Would something like this change? Because these are the sorts of things that we tend to look at as well. And it's giving you a very clear year signal, but also a time signal.
yeah,
And, you know, the predators, the avian predators are occurring at a particular time.
right. Yeah, it's gonna,
It will kink it to some.
it'll kink it, yeah. I don't, and it kind of goes back to that. I think the degree of that is gonna be, there's that plot, how the recoveries changed over time. And I think that when you lay that on top of the year effects, that it could create some kind of, you know, correlations or something in there that you may pick up from another covariate. I don't know, or it's just going to add more noise. But I think that the component that there's the arrival component. I mean, even if you didn't account for avian predation, just the fact that having travel time in there and the arrival probability at the ocean, I think helps with this right here. Okay, so then what else we got? Yeah, so one thing again, I want to go back to those simulations and quantify this stuff that we're talking about, that, you know, what happens when you don't include these things. And then, you know, try to find ways, if there are some other tricks to potentially, you know, make those things more identifiable. And that's going to have to be with some either additional assumptions, additional data from acoustic tech studies or something, and then maybe some, you know, tightened priors or something. But that would have to, you'd have to be well justified to do that. But then, yeah, so Chinook with mini jacks, I've coded that up and run it, but I don't have results from that yet. Then different models for ocean survival, predation rates, could throw in transported fish to add more data. Could throw in fish that were, I mean, right now we're just limiting to fish that were detected at Bonneville or Troll. You could actually add all fish that were tagged upstream, and then, you know, they may never be seen at Bonneville or Troll. They could come back as adults, and I mean, I don't know. You could, it becomes a huge. These things already take quite a while to run, so the more data you add, the more harder it's going to be. Well, I was just running the Chinook one. I was going to see if I could get results for this talk, but it took too long to run. I started it on Thursday, and it ended. I don't even know if it ended last night. It was almost there. So we have this Linux server, and it has like 128 cores on it, and I was using 50. I ran 50 chains simultaneously, and it took over 4 days to run. So it chugs along, but I mean, and if you add a lot more data, it's going to take a heck of a lot more time, but it's not too bad, really. I mean, for what comes out of it, it's not too bad. And then, yeah, I'm potentially including length and hatchery wild. That definitely you would get. I mean, those would be things to add potentially. Definitely rearing type, I think. Okay, next. Need to thank real-time research for the data, and the guys at USGS kind of came up with some of the things that I kind of took and pieced together in different ways, and EPA helped fund this. Then I don't know if anybody, the next slide, I was told I should put this in here. So we have 2 positions.
I'm going to give the little spiel about don't work on Wall Street thing.
Yeah, don't work on Wall Street. No, we actually have.
Actually, you go. I'm not going to get a job.
Okay.
Thanks, that was great.
Yeah, thank you. Thanks for the feedback. That was really good.
You should have had that bit with Wall Street. We were laughing. I showed.
I didn't see. What was that?
You didn't. It was
Just a job ad.
It was a job ad, but it said like, do you want to work?
Oh, I did see that. I did see that, right?
I honestly don't. I don't want to go there. Anyway.
Thank you. So yeah, we have 2 contract positions opening. One is PhD statistician. Going to help get some the things that we need to get out the door, some stuff similar to this that we're working on here. And then ecological modeler, working on mostly a hydropower system related stuff. So if you or you know anybody, would just be aware that these could be coming out, right? I shouldn't say these are for sure, but I just want to put it on your radar that these could be coming around in a couple months. That's all I got. Any other questions or anything?
Do you have any questions
Yes.
online?
Can you remind me what's in your PC1 for the ocean conditions? Maybe you mentioned it.
Oh, God. So I think that's driven a lot by temperature. The weightings, I haven't looked at that in a while. And
I was just curious because you said that once they get into the ocean, then there's sort of things that eat them.
yeah,
But then already at that stage, that's mortality comes from predation, right? So I was kind of wondering on your slide on the next steps, you had thinking about the ocean conditions and what variables could be useful there. Have you thought about, say, hake abundance or some index thereof?
yeah, I mean,
Would it be useful?
I think that would be useful. And with ocean temperatures, that predator component changes. So that part, I think there's a lot of things baked into temperature, right? So there's stress, there's food availability, oxygen, and then there's, predator complexes, because all these squid show up, when the temperatures are warmer, or, these populations shift and move around. And so, yeah, there's a different suite of predators, and it would be useful, I think, to have that. We do this JSO survey twice a year. We used to collect, there were several years there where we were running the trawls at night, and so we called the predator survey because a lot of fish are coming up vertically migrating, and you're catching them at night. And so we had some indices of abundance for those fish, but we stopped doing that for time and cost reasons. But yeah, and like I was mentioning earlier, there's some birders that go out every year, and they're doing surveys of the shearwaters and the mures and stuff that are out there in the plume every year, and they're not coming at the same time. Like the shearwaters are coming up from New Zealand or something, and they may come to California first and hang out there some years longer if they got good feeding before they come up. So they're not showing up at the same time, and I think that would be an interesting thing. Like those shearwaters, they're all over out there in the plume, and they're really hitting the salmon when they come out. So that could be informative. But there's just so many things, so many things going out there. But so many unmeasured things that you just, you got to use it. Oh, PDO is going to help to explain something, but it's just really far removed from what's really happening in there.
At least a few of those are probably redundant as well.
Right. Yep. That's why, using principal components can help, get information out of the ones that are really correlated across, but it's not satisfying. There's a lot more we could do. Yeah. Any questions online?
We have a question online. Rebecca Buchanan said, "Great presentation, Jim. Could the avian predation occur upstream of the towed array so that recoveries may not necessarily mean survival in the towed array?"
That's a great question. I made the assumption that they're not. I know that they do, but we could definitely build that in. We have models for avian recovery, and Quinn Payton has done this too, where you have to account for the fact that, okay, the fish could, birds could have came and took fish from one reach and then brought them back to somewhere else. to a colony. Like that happens in the mid-Columbia a lot. But yeah, that's a complication that I didn't want to address for this particular model. But you're right. I mean, it could certainly be the case that they are going above the trawl and fishing and bringing fish back to the colonies. But I think we're fairly safe in making the assumption that that doesn't happen very often. Maybe I'm wrong.
Any last questions online? Okay, looks like that is it. Thank you so much for presenting today, Jim.
Thanks, everybody.
Thank you. Good work.
Thank you.